Yes,
Okay.
yes. Thank you very much. Please.
Welcome. So, thank you, John and all friends. Great pleasure for me to meet all of you. So, I have a presentation which is a little bit technical. So, I try to, before starting, to give some information about the objects, mathematical objects we have to look in the presentation. So the title is Fractional Parametric Dynamical Models. It's a joint work with Diego Caratelli and Pierpaolo Natalini. Understanding change with mathematical models. The world around is constantly changing, from the fluctuation of stock market to the growth of forests and many phenomena over time. To understand, predict, and even control this change, mathematical scientists use dynamical system. A dynamical system is simply a way of describing how to the state is changing. For example, temperature of the room, number of animals in the area, and so on. Change over time. These systems can be incredibly complex, non-linear, or more manageable when they are classified as linear. In this presentation, we will explore several extensions of the classical theory of linear dynamical system and the fundamental role in modeling population dynamics. Some premise is necessary, and I try to skip this one. Oh, sorry. Oh, now it's better. Okay. We have some type of definition here. It's quite obvious that the definition of the exponential function is simply connected with the derivative operator, since it is an eigenfunction of the derivative, this formula here. In what follows, we can use different types of exponential functions. These different times always satisfy an equation like this one. The derivative, generalized derivative, satisfy an equation like this. The examples are the Laguerre-type derivative, which is given by this formula here, in which the denominator is the k factorial to the square, which is an eigenfunction of this operator. This is called the Laguerre-type operator. This operator is given by dx plus x, the second derivative. So if you apply this operator to this function, we recover the same function multiplied by the parameter. Another generalization is the nth order Laguerre-type derivative, in which the denominator is raised to the power n plus 1. This is the n-type Laguerre-type operator, which is given by a formula like this, more complicated, in which there are several derivations and multiplied by this coefficient, which are singly numbers of the second kind. This function satisfies a similar equation in which if you apply this operator to this function here, you recover the same function multiplied by the parameter. Another type, so this is a remark in which is written that this operator is not completely new, since it was previously known by several authors, but in quite different form. There is an isomorphism, which was recalled in the paper by Pino and myself, in which there is a differential isomorphism, to denote by this symbol here, acting on the space of the analytic function of the x variable by means of this correspondence. The derivative is substituted by the Laguerre derivative, and the multiplication is substituted by the antiderivative, which is simply the primitive of this function. In general, the n primitive is like this, and if you apply this operator to the antiderivative, we find x to the n over the factorial of n. So applying this isomorphism to the function e to the x, the classical exponential, we find the first Laguerre-type exponential. And if you iterate this function, this operation, we find the second and so on. This type of computation gives that if you apply the Laguerre-type derivative to this power, you find this power multiplied by n, and the exponential is raised to the power n minus 1. And so if you apply the antiderivative, you find this equation. This means that the Laguerre derivative is a derivative operator for the polynomial family, x to the n over the factorial of n, and the antiderivative is a corresponding multiplication operator. This is in the idea of Datley to use this correspondence to construct a different form of powers. The factorial exponential function is another type of fractional exponential function, is another type of exponentials. Given any number alpha greater than 0, the fractional derivative is a definition by we use the Euler definition. It is written here in this form. Applying the fractional derivative to the power x to the n, we find the ratio of two gamma functions multiplied by x to the n minus alpha. This is when alpha n is greater than ceiling function. This is the first value of minus 1, and is 0 if the values of n is up to the ceiling function alpha minus 1. It's interesting that if C is a constant, the fractional derivatives of the constant is 0, like in the classical case. This is for every alpha greater than 0. This is a particular case of the so-called Caputo fractional derivative, which is expressed in this formula in which there is in integral form. It's more complicated. But this equation reduced to the preceding equation with alpha equals 0 and f is the power x to the x, classical power x to the n. The fractional exponent function, depending on alpha, is given by this form, which is completely similar to the classical exponential, in which instead of the factorial, we have the gamma function, because if alpha is an integer, this is just the factorial of this integer. And this is an eigenfunction of the fractional operator, since if you apply this fractional operator to this function here, you recover the same exponential multiplied by t to the power alpha. The contents of the article is a little bit complicated, so I will try to skip the proofs and some more complicated things. It gives us an idea of the content of the article. Introduction of different types of exponential functions with aggregate functions of suitable different operators had been possible to extend the classical mathematical problems identities such as the linear dynamical system, the Bernoulli and Euler norms, and polynomial population dynamics models, and the Laplace transform. In particular, the Laguerre-type derivative we have shown before, the fractional derivative, and the parametric version of these operators have been used in this context. In this lecture, we consider the case of fractional and parametric, both of this generalization, exponential operator, to derive the corresponding dynamical models. Numerical example of some of the models examined, derived by the first author by Diodo, using computational algebra problem Mathematica, are shown through the article. So this idea starts from a paper by Indian mathematician Abhishek Mishra, who proved that this function here satisfies this equation. This means this is the ordinary derivative. As if you apply the ordinary derivative to this function, you will recover the same function but with the shift of the parameter. Instead of m, you have m plus 1. This is similar to the exponential but with the shift of the parameter. This is a particular case of more general operator introduced by Parametric. But the idea of Pino in old article published in Georgian Mathematical Journal is that this function here is it's exactly the same function, is an eigenfunction of this operator, which is the Laguerre derivative plus m times derivative, ordinary derivative. The t means the ordinary derivative. For every complex c, if you apply this operator here to this function, the function of Mishra, the same of before, you recover the same operator, the same function multiplied by c. So this means that this is eigenfunction of this operator. This makes it possible to apply, to generalize several dynamical systems, in particular those related to the population dynamics, substituting the ordinary derivative to this Laguerre-type derivative contain this parameter. So you find more general evolution problem. The problem is that in general, when you deal with the fractional operator, it's not sufficient, like in the previous case, substituting the denominator by the, for example, for the square in the case of the first order. Because this doesn't work. This was observed by Diego, who was able to prove that this square must be replaced. Instead of gamma square, you have to put gamma multiplied by this function. This function is defined in a more complicated way. This is this m plus 1 over m plus gamma alpha plus 1 with k over 0 is 1 with k over 1 is given by a complicated product when k is greater than 2. Introducing this function, the function lambda, put here in this denominator, we proved that this function here, with which we use the fractional derivative, in some sense is a generalization of the previous operator to the case of the fractional operator, in the fractional case. For every complex constant c, you apply this operator fractional, parametric fraction, because there is also the parameter, to this function here, 5, you recover the same operator multiplied by c to the power alpha. So means this is an eigenfunction of this function. This is a proof. The proof is quite technical, I skip it, of course. The proof is based on the fact that this factor here is equal to 1 because of the definition of the function lambda we have shown before. And also it's worth noting that this function lambda k appears as an extension of the Pochhammer symbol. Pochhammer symbol of a number is increasing instead of decreasing in the case of factorial, we have increasing powers. And so Pochhammer of alpha is alpha times alpha plus 1, alpha plus 2, alpha to n minus 1, the n to Pochhammer symbol. So this is a particular case of the Pochhammer symbol. The application of this generalized operator to the classical case is like this. This is the classical result using derivative, ordinary derivative. If you have a matrix R by R, and you consider this evolution problem, the derivative is the matrix times this is a matrix matrix is a system, of course, because this is a matrix. The solution of this problem with the initial condition zeta 0 is given by this formula here, in which the coefficients satisfy a recursion. The first one is I, the identity, alpha n a is r time a time alpha n minus 1 of the function. Then we have the recursion for computing the coefficient. So there is also a possibility to write the solution in a closed form. This is a classical result because the solution depends on the exponential of this matrix. And if you apply the exponential of the matrix to the initial value zeta 0, there is a closed form which is very classical, in which we use the characteristic polynomial of the matrix T times A, in whose coefficients are also the invariants, called the invariants of this matrix, and we use a contour, gamma is a contour, enclosing all the eigenvalues of this matrix. So it's worth to recall that this contour can be constructed without knowing the eigenvalues. It's sufficient to know a region of the plane in which these eigenvalues are contained, and which can be done by using the Gershgorin circle theorem, which is a classical result. So if you generalize this this problem to the fractional parametric linear dynamical system, you have to introduce, instead of the isomorphism we have shown for the Laguerre-type exponential, a generalized isomorphism, in which if you apply to this generalized isomorphism to this power, you find the t to the k in this form, in which here appears just the function lambda we have defined before. So if you consider this problem, the solution of this problem is given in this form, which is a generalization of the solution of the linear dynamical system solution. And also this is the proof, but I skipped the proof. The theorem is like this. Consider the Cauchy problem for the fractional linear parametric dynamical system like this, in which we need two initial conditions. But this is the matrix in the condition, of course. R is R by R given matrix, and this is the fractional parametric derivative defined in this form here. You can see just the operator we have shown before. The solution also can be written in the classical formula generalizing the previous result, in which instead of the operator exponential here, there is the function we have defined like an eigenvalue of the operator. So the result is just the same. This problem has been applied in a working example. For example, we consider 3 by 3 system. This is the matrix 3 by 3. You know the invariance, the trace, the sum of 2 by 2 principal square minors, and this is equal to 1. The third invariant is the determinant is equal to 2. So if you apply the initial condition, you find the solution. And it's possible to find the shape of the component of the solution. And we are checking here for various values of the parameter, but in the paper we show only the case m equal 5, we have 3, and m equal 20. We have found. Now, the preceding results are applied for classical, generalized classical linear dynamical system, in which instead of the ordinary derivative, we put the fractional parametric Laguerre-type derivative, this operator here. In the Malthus model classical, we have only the derivative here, and we have the solution like an exponential. And in this case, putting two initial conditions, find the solution in two form, in form like a recursion. It can be found like a recursion of the coefficient, but we can also find in the closed form, which shows that the solution extends the classical case. Another case, very traditional, is a fractional. The ordinary is known as a Verhulst model, but in which we have only the derivative, ordinary derivative. If you put this operator more complicated, which is fractional and parametric, we have this equation, which put two initial conditions like this. And in this case, the Verhulst model arises then observing that the environment is not infinite resources, so we have a limit of the resources. This limit is given by this constant k, constant k. And in this generalizing to the fractional parametric case, we have a more complicated expansion, but we've always used this form instead of gamma and gamma square or gamma in other terms. We have to put the function defined by Diego. And using this function, we find the result. The coefficient of the expansion for the solution satisfy this recursion. So this is so big that we put into lines, but you have an initial value, and the ak plus 1 is r times ak. This is a power multiplication of the coefficient, and also the denominator is quite complicated, but then it's possible to see in some cases. This is the proof. So the proof is very simple. You apply this operator, make all computation, and compare this one with the second member, and this gives the recursion of the coefficients. We have here an example, sorry. Yeah. Considering the Verhulst fractional parametric Verhulst model, the expansion of the coefficient are given by the coefficient of this one in the particular case we will consider. Is impossible to see because this I can sorry. It's impossible to see because there is okay, now it's possible. Assuming the values of the parameter m equal to r and k, given putting the initial condition 1, the solution is given by the expansion we have seen in the previous slide, whose coefficients are reported in this table here. The graph of the solution using the coefficient reporting in the preceding table are given in figure 8. Figure 8 is here. It's possible to see how to evolve the solution over time. The other classical problem is the so-called minimum threshold logistic case. Logistic is a Verus also called. The Verus case is also called the logistic case. The minimum threshold means that not only the resources of the environmental are limited by indicated this parameter here, but there is another parameter, capital M, because capital M denotes the population minimum threshold under which the population goes to extinction. It has been detected that each population of some animal becomes lower than a level, a given level, they can't improve. And so they are destined to the extinction. So this is introduced by this parameter capital M. Assuming this condition here, initial condition, and also always considering the solution in some particular form, which is the previous form, like expansion with AK coefficients, and in which into the denominator appears the lambda k function defined by Diego, it's possible to find that the solution of the minimum threshold model, fractional minimum threshold logistic model, satisfy this coefficient by this recursion. This is the first coefficient, the second, and the k plus 1 is given by this form. The proof is always the same. You put the solution in the form we have seen before. I show you again. This is expression 27 here. Using this expression, you put the solution into the equation, compute the fractional derivative, and also all things are needed, and you compare the two members and you find the recursion for the coefficient. This is an example. Assuming m equal 2, r equal 1, k equal 2, m equal 2, putting the initial condition 1, the solution of the fractional parametric logistic minimum threshold model. For alpha, also we have put the value for the value alpha, is given by this expansion before, with coefficient are given by this table. And the graph of the solution is like this. The other important model which is studied, the classical case, is a so-called Lotka-Volterra model, and in which you have the two populations which are competing for survival. And the classical Lotka-Volterra, we have here a derivative, ordinary derivative, also here. And there are two populations, X and Y, and the system is like this. Since the solution of this problem cannot be written explicitly, the solution is studied in the so-called the orbit of the solution. It's only possible to find the orbit of the solution, which are closed curves surrounding the equilibrium point, which is given x value x at 0 and y at 0. And the equilibrium point is the same of the classical model. It depends on the parameter s and beta, S and R and beta, S and gamma. These are the four parameters which appear in the system. And the following theorem holds, putting again in the same form the two solutions, x and y, the solution of the fractional parametric Volterra model under the initial condition x0 and y0 is obtained by recursion for the coefficient. This is the a0 and b0, and ak plus 1 and bk plus 1 are this form in which c or k is given by this more complicated expression. And the proof is always the same. It's sufficient to use the expansion in which you search the solution, put in performing compilation in the equation, the system of the two equations, and comparing the coefficient, the members of the system, resulting system, you find the recursion for the coefficients. An example is like this. Assuming this value of the parameters, ms, beta, gamma, and so on, and the solution, the graph of the coefficient given the solution are two curves which are intersecting in both one or the other. Conclusion. A Laguerre-type operator containing a positive real parameter which behaves as an exponential with respect to its eigenfunction has been used to extend some classical models of population dynamics to the fractional parametric case. The eigenfunction of the fractional operator cannot be obtained by simply replacing the factorial with the gamma function in the eigenfunction of the ordinary operator, but required a more deep analysis. As a result, the greater complexity of the recursion formula for the calculation of the coefficient of the related solution has been detected. The analytical and graphical results shown with the aid of the computer algebra system Mathematica have confirmed the possibility of using such models which can allow a better fit to real data. So we mean that using this parameter in a practical case should be possible to improve the solution and fitting better to the real data. So there is a little literature starting from the classical result, Ali, Baker, so. And we use the paper by beginning Caputo for the definition. And we also have in past time some special case, the study of Laguerre-type special function in population dynamics, and also several papers by Caratelli and myself. And this is important, the book of Cherubino, in which the formula using the contour integral is used and shown. And these are the preceding paper by Dattoli, and also this in which the operator Laguerre-type parametric operator is also introduced, and this idea of Dattoli, of course. And there so also some preceding work by myself and some students, and these are the paper in which the operator Laguerre-type are also considered, but in some different form. This is Gammacher, very famous matrix theory, and also the book of Kirjakova, in which recall the preceding work of Delvaux, Dimosky, and Litkin. And it's a work by Mishra, in which the pseudo exponential function is introduced. And so also Bramkard, and and also Ilico and myself, in which we studied also introduction of operation and special polynomials, in which I recall several papers which have been used in my work. So this is all. I apologize for more very technical presentation, but I was not able to find easier form to present it. So thank you again.
Okay. Thank you, Paolo, for this. It's a technical presentation, that is true.